So for our next topic, we're going to discuss momentum. So usually when we hear the term momentum, this is usually referred to or commonly used term in sports. So a team that has the momentum is on the move or is going to take some effort to stop. A team that has a lot of momentum is really on the move and is going to be hard to stop. Momentum is also a basics term. It refers to the quantity of motion that an object has. A sports team that is on the move has the momentum. So lumalaban sila. If an object is in motion or on the move, then it has momentum. Momentum can be defined as the mass in motion. For us to understand momentum better, I have here a video presentation. Let's watch.
So, like the Newton's cradle, the impact of one ball on another produces a compression wave that goes through the ball. Any efficiently elastic material from steel to a rubber ball will do this. I have a really good way to show this by adding a different ball into the mix, a water balloon. I'll also need to show some slow-mo science with the help of Darren, the man who can slow down time, and some help from a fellow science enthusiast named Trevor, a middle school student.
It's pretty cool, huh?
Very cool.
Okay, Trevor, so you saw when we did the Galilean cannon, all those
Yes.
balls stacked up on one top of another?
Yeah.
So we're gonna look at that in an interesting way, because I have a water balloon here, and we're gonna use a tennis ball, okay? So actually, you're gonna do this. So here, hold this balloon, and you wanna stack this on top. On the count of 3, I want you to drop it, and we're gonna observe what happens to the tennis ball, okay? Okay, ready? 1, 2, 3. Drop. There we go. Perfect. So what did you observe?
That when you dropped it, the tennis ball shot up.
Exactly.
Energy.
Because all of the momentum from this water balloon was transferred into that tennis ball and shot it right up in the air. Now, Darren has his high-speed camera, so we actually can watch that happen in slow motion.
Let's watch it. Whoa.
Yeah, isn't that cool?
That's like shooting go in slow motion.
Just like
your lips
that.
go.
But what's cool about this is that the water balloon kind of highlights where the energy is transferred. So you see how the ball kind of floats down with it, and then it sucks in and pushes it away?
Well, when you take the balloon and you put the tennis ball on top and you drop it, the energy from the balloon transfers into the tennis ball and shoots it up. It looked like the balloon supersized the bounce. I thought the demo was very cool, especially the slow motion.
So you like science?
Very much so, yes.
I'm glad to hear that. What's your favorite area of science to study?
Probably life science.
Yeah, it's important to learn about living things.
Very much so, yeah.
Well, I appreciate your help, man. Thank you very, very much.
You're welcome.
Okay, so in the demonstration a while ago, we have seen that the transfer of momentum from the water balloon causes the tennis ball to shoot up. So that is what we're going to define for this lecture series. So for this lecture series, our objectives are the following. First, we are to relate the motion of center of mass of a system to the momentum and net external force acting on the system. So these are some big words, but do not worry, we're going to discuss them one by one. Next one would be to relate the momentum, impulse, force, and time of contact in a certain system. Next one is to compare, contrast elastic and inelastic collision. So this would be much better done when we try to compute for them. Last one is to solve problems involving the center of mass, impulse, and momentum. First, let us define what is a momentum. So momentum can be defined as the mass in motion, meaning you have your mass, a certain object has a mass, and it is actually moving. Remember that all objects have mass. So if an object is moving, then it has momentum. It has mass in motion, very simply defined. The amount of momentum that an object has is dependent upon two variables. First is how much stuff or the mass is moving and how fast the stuff is moving. Momentum depends upon the variables mass and velocity. In terms of an equation, the momentum of an object is equal to the mass of the object times the velocity of the object. So that is what we can see in this formula here. So the unit of momentum is written as a lowercase p, mass as m, and velocity as v. So the equation illustrates that momentum is directly proportional to an object's mass, which means that the bigger the object is, let us draw that one here. If we have here object 1, let's call it m1, and object 1 is larger than object 2, which means that m1 will have a greater momentum than m2. Another thing is momentum is directly proportional as well as the object to the object's velocity, which means that if we again illustrate that, if you have m1 and m2 with the same mass, however m1 is traveling the velocity of, let's say, 10 meters per second, meanwhile m2 is traveling at a velocity of 1 meters per second. Since m1 has a higher velocity, it would mean that m1 would also have higher momentum. Meanwhile, m2 has a lower velocity, which means that it will have lower momentum. As simple as that. So the units for momentum would be mass units times velocity units. The standard metric unit for momentum is written as kilogram meters per second, which makes sense since momentum is equal to mass, which has the unit of kilogram, and velocity, which has a unit of meters per second. So while the kilogram meters per second is the standard metric unit of momentum, there are other variety of other units that are acceptable, though not conventional. So they are not usually used in momentum. Examples are kilogram per miles per hour, kilogram kilometer per hour, also gram per centimeter over second. In each of these examples, a mass unit is always multiplied by a velocity unit to provide a momentum unit. This is consistent with the equation for momentum here, as we have discussed a while ago. Take note also that momentum is a vector quantity. So if you can recall, if it's a vector quantity, it should have both magnitude and direction. So it means that to fully describe the momentum of a 5 kilogram bowling ball, as we can see here on this GIF, let's write it down. P, 5 kilogram bowling ball moving, let's write it down. Mass is 5 kilogram and moving westward. This time it's eastward, meaning going to the east. It's a velocity 2 meters per second. You must include information about both the magnitude and the direction of the bowling ball. So it is not enough to say that the ball has 10 kilogram meters per second of momentum. So it wouldn't give us the complete information with regards to the momentum. The momentum of the ball is not fully described until the information about its direction is given. So the direction of the momentum of the vector is the same as the direction of the velocity of the ball. Since mass is a scalar quantity, it doesn't matter kung ano yung direction ng mass because it wouldn't have any direction. Meanwhile, velocity is a vector quantity. In a previous unit, it was said that the direction of the velocity vector is the same as the direction that an object is moving. So if the bowling ball is moving eastward, as we can see here, it's going east, then its momentum can be fully described by saying that it is 10 kilogram meters per second east. So as a vector quantity, the momentum of an object is fully described by both its magnitude and direction. To further explain momentum, let us again define it. Momentum is mass multiplied its velocity. So it becomes obvious that an object with a large momentum, if both its mass and velocity are large. Imagine, for example, if you have here a Mach truck. Imagine if this truck is moving at a velocity, let's just say, of 30 kilometer per second. Consider a Mach truck here, and we have here a roller skater moving down the street at the same speed. Let's say that this roller skater is also moving at about 30 kilometer per second. Now, the considerable greater mass of the Mach truck, this one mass, let's just say about 1,000 kilogram. Hinuhulaan ko lang. And this has a mass of, let's just call it mass 1, mass 2. Let's have his, for example, 50 kilogram. Again, the considerably greater mass of the Mach truck gives it more momentum than the least massive roller skater here. Yan. Again, since they have the same speed, however, this truck has a larger mass, it will have greater momentum than this one. Let's draw it as a small arrow. Yan. Yet, if this truck, for example, goes to a halt, so it will have 0 kilometers per second, what will happen is the momentum of this truck will now be 0. So P would be equal to 0. Remember that the momentum of any object that is at rest is equal to 0. Since P is equal to m multiply the change in velocity, if this is 0, whatever you multiply it from would be equal to 0. Remember that objects at rest do not have a momentum. They do not have any mass in motion. Both variable mass and velocity are important in comparing the momentum of the two objects. The momentum equation can help us think about how change in one of the two variables might affect the momentum of an object. Okay, to check our understanding further, we have here several examples. First is we are to determine the momentum of a 60-kilogram football athlete moving east at 9 meters per second. So let's write down our formula. Momentum is equal to mass multiply the change in velocity. So this would be the mass of the athlete is 60 kilogram. I'm not going to write the unit to make it more cleaner. And it's moving about 9 meters per second. So that would be 9. So you multiply that, you plug that in your calculator. Let me get my calculator. 60 times 9, that would be 540 momentum units or kilogram meters per second. Don't forget the direction, which is east. Next, 1,000 kilogram van moving north at 20 meters per second. And a freshman moving south with a mass of 40 kilogram. I'm going to give you a few moments to answer. Please type your answer on the chat panel. Okay, so I hope you're done. So for this, we have here 1,000 multiplied to 20. So that would give you about 20,000 kilogram meters per second north, since it's moving northward. Letter C, we have here 40 multiplied by 2. That will give you 80 kilogram meters per second moving south, so the answer would be south. So as simple as that in calculating momentum. Let's have another example. A car possesses, sorry for that, a car possesses 20,000 units of momentum, meaning 20,000 kilogram meters per second. What would be the truck's new momentum if its velocity was doubled? So we're going to do logic here. Since velocity is directly proportional to momentum, if you double the velocity, it would also mean that you are to double your momentum. So you're going to have 40,000 units or 40,000 kilogram meters per second of the velocity. of the momentum rather. If the velocity was tripled, still velocity is directly proportional. If you triple this one, you multiply it by 3. This would also be multiplied by 3, which means you're going to have 60,000 kilogram meters per second. Direction is not given in this scenario, so we don't have to write it down. If the mass is doubled by adding a greater load, so why is it emphasized here? Because usually, if an object is already moving, it doesn't change mass. For example, if you are running, you don't you don't you don't double your mass. Okay, usually, velocity changes if you want your momentum to increase or decrease. However, for example, at this one, you have a truck and then you put a greater load. If you double that mass, what will happen? Same thing. Since according to our formula here, it's directly proportional. If you double your mass, you are also going to double your momentum of 20,000. If both the mass and velocity was doubled, what will happen? You are going to also have doubled value for each since you multiply both of them by 2. Remember that doubling the velocity will double the momentum and doubling the mass will also double the momentum. The combined results of doubling both momentum and velocity will double twice, which means you are to quadrupled it. That's why your answer is 80,000 kilogram meters per second. Okay, remember that there's a certain law in momentum which states that momentum is always conserved. The law of conservation of momentum says that the momentum of a closed system is constant in time or simply conserved. A closed or isolated system is defined to be one for which the mass remains constant and the net external force is zero. The total momentum of a system is conserved only when the system is closed. For short, several scenarios will conserve momentum such as this one, which means the initial momentum should be equal to the final momentum. For example, if you have here a car moving in this direction and you have, let's say, another car also moving in this direction but probably slower, and then if this car hits, so yeah, if this car hits the other car, and they both move in this direction, the momentum on this first scenario A should be equal to the second scenario B. So we are going to prove that on our calculations. Let's have some example. First is this one. We have two bodies, M1 and M2, which is on a collision. So usually when we talk about momentum, um, it, it's connected to the concept of collision. So collision is simply when objects collide with each other. It's as simple as that. So in this example, we're going to try to use the concept of momentum conservation, which states that again, the initial momentum should be equal to the final momentum to search for the final velocity. So M1 has a mass of 1 kilogram and is moving at a velocity of 10 meters per second east. Meanwhile, M2 with a mass of 3 kilogram is at rest. So M1 hits M2. We are now to determine the final velocity if the two masses stick together after the collision. And this is important. When we talk about stick together, again, we have elastic and inelastic collision. In the future topic, we're going to have examples with both of them. But for now, we are to have we are to assume that they stick together. Okay, so let's illustrate that by drawing M1 here. Okay, so M1 has a mass of 1 kilogram and it's moving at a velocity of 10 meters per second. Meters per second to the east. So since it's to the east, the 10 meters per second would be positive. Again, momentum is a vector quantity. Meanwhile, the other object, M2, with a mass of 3 kilogram is at rest. So the velocity of M2 is 0 meters per second. So in this scenario, what happens is that M1 hits M2, and then after M1, I should have drawn this a lot larger. So let's try it a little larger here. So after it hits M1, what happened is that they stick together, katulad nito, and then we are asked what will be the final velocity. Okay, what will be the final velocity of both of, since they stick together, can assume that they are one object. So how do we attack problem like this? Again, we have already illustrated our scenario. This is the first scenario. This is the second scenario. Okay, so for this, we are going to go back to our concept, which states that the initial momentum should be equal to the final momentum according to the momentum conservation. Now, momentum or PI is also actually the mass of object 1 and the velocity of object 1. Again, remember that the definition of momentum is P is equal to the mass, then the change in velocity. So here, initial plus the mass of the second object, and then the velocity of the second object initial should be equal to the mass of the first object and velocity of the second of the first object final plus the mass of the second object, velocity of the second object final. So what have we done here? We have simply here we have just simply enumerated the different variables. So remember that the momentum on this object, which is pi here, should be equal to the momentum of the final momentum or final scenario. So what we want to do is to isolate the final velocity. So we are going to write it as this one. We're going to write m1 v1 initial plus m2 v2 initial is equal to m1 plus m2 multiplied by the final velocity. So why have we done this? Simply because according to our second scenario here, they stick together, which means we can treat this object as one by adding their mass. Okay, that in that way we can search for its final velocity. From here, it's just a matter of algebra. We don't have to isolate VF. To do that, we simply divide both sides by their masses. M1 plus M2, cancel, and I'm just going to transfer VF on the other side. Our final formula with P, the final velocity would be equal to M1 V1I plus M2 V2I is equal to the mass of the first object and then the mass of the second object. At this point, we just have to write down or substitute our values. M1 or the mass of the first object is 1 kilogram. I'm going to drop the units to make it more simpler. Multiplied by the velocity of the first object, which is 10 meters per second, plus the mass of the second object, which is 3 kilogram, multiplied by its velocity, which is actually 0 meters per second. And then divided by the mass of both objects, 1 plus 3. So from here, That would be 0. This would be 10. You're going to have 10 over 4. So the final velocity is 10 divided by 4. That would be 2.5 meters per second. Okay, so again, we're talking about velocity, so the unit should be meters per second. And as you can see here, it's a positive value, which means that it would be towards the east or to the right. Ibig sabihin nun, when M1 hits M2, both of them will have to move to the right at a velocity of 2.5 meters per second. Meaning, napahinto considerably ng M2 yung bilis ng M1, which is 10 meters per second. Okay, so that's how you find velocity. Let's have another one. So for number 2, we have two bodies, M1 and M2, which is on a collision. M1 with a mass of 3 kg is moving at a velocity of 10 meters per second east. Meanwhile, M2 with a mass of 1 kg is moving negative 70 meters per second west. So this time they are both moving and they have different velocities. Determine the final velocity if the two masses stick together after the collision. So actually you can think of it as a road accident with a smaller object and a larger object. So let's, but for now, let's still draw our boxes here to represent them. So this would be M1. So it's moving at a velocity of 10 meters per second east. So it's moving to the right at a velocity of 10 meters per second with a mass of 3 kg. Let's write it as M1. That's our given. Then another one would be the second object, which is M2 with a mass of 1 kg, smaller, but with a velocity of negative 70 meters per second. So it's negative since, again, something like that, it's moving to the west. Okay, so according to this one, they hit together, then we are to determine the final velocity of the two masses. So we still have the same logic a while ago. We are to write down that initial momentum should be equal to the final momentum. Expounding this, we're going to have the momentum of the first object, initial, plus the momentum of the second object, initial as well, should be equal to the momentum of the first object, final, plus the momentum of the second object, final. Still, we are trying to search for the final velocity. Okay, same as the last one, since the object sticks together, what will happen is that this will stay. Meanwhile, we can now add our masses, since again they stick together, and then we can just put our VF here. Okay, so we only have one VF, again, primarily because they stick together, meaning their velocity should be 1. So divide both sides by their masses, cancel. M1 plus M2. We now have our formula, VF is equal to M1V1I plus M2V2I is equal to M1 plus M2. So writing down our values here, we're going to have 3, which is moving at 10, plus 1, which is moving at negative 70. We have to write the units since, again, we're talking about momentum, which is a vector quantity. Then 3 plus 1. So putting that in your calculator, you're going to have 30 minus 70 over 4. That will be about negative 40. Negative 40 over 4, which will give us the final velocity of negative 10 meters per second. Negative, that would means to the west or to the left. So that's how you search for the final velocity, knowing the value of knowing the concept of conservation of momentum. In our next few topics, we're still going to compute for what will happen if it's an elastic collision and the concept of impulse. So we are now on our topic, which is momentum and impulse. So as mentioned in our previous discussion, momentum again is commonly used term usually in sports. Again, when a sports announcer says that a team has momentum, they mean that this team is really on the move and it will be hard to stop them. Again, momentum is a physics concept. It means that there's an object which will be hard to stop. And for us to be able to stop that object, we need to apply a force against it for a given period of time. Remember that the more momentum that an object has, it will be harder to stop that object. Thus, it would require a greater amount of force or longer amount of time or both to bring such object to a halt. Just imagine, for example, if you have the structural integrity to make a truck stop just by pushing. For example, hindi kayo madudurog for some reason. It will still be hard for you to stop the truck. You have to take more force of pushing, and then it will not actually eventually come to a halt. It will still move for a certain period of time. And then as the force acts upon the object for a given amount of time, the object's velocity will change, and hence the object's momentum will also change. This concept is not an abstract information for us. We can also observe this a different number of times when we watch sports, diba? Or for example, American football. When a defensive player tries to apply a force for the offensive player na tumatakbo, di ba minsan niyayakap pa nila? And bago nila mapahinto actually yung offensive player. Another thing is that when you are on a car or when you are driving a car, as you bring your car to a halt when approaching a stop sign or a red light, the brake serves to apply a force to the car for a given amount of time. And this results to the change in car's momentum. Remember that an object with momentum can be stopped if a force is applied against it for a given amount of time. A force acting for a given amount of time will change an object's momentum. If we put it another way, an unbalanced force always accelerates an object. If you can recall the second law of motion, either by speeding it up or slowing it down. Now, if the force acts opposite the object's motion, it slows the object down. And if a force acts in the same direction as the object's motion, then the force speeds the object up. Either way, a force will change the velocity of an object. And if the velocity of the object is changed, the momentum of the object will also change. This concept is known as the impulse. If you can recall, this is just an outgrow of the Newton's second law of motion, as discussed in our earlier unit lesson. The second law of motion states that F is equal to ma, or that the acceleration of an object is directly proportional to the net force acting upon the object and inversely proportional to the mass of the object. That's F is equal to m. F is equal to ma. Now, when we combine with the definition of acceleration, here, acceleration is simply the change in velocity over time. which means that F is equal to ma is also equal to F is equal to m multiplied by delta V over time. Now, if both sides of the equation is multiplied or are multiplied by the quantity t, a new equation will result. So if we multiply this both sides by t, this will cancel out each other, and then you're going to have your t here. So you're going to have F multiplied by t is equal to m multiplied by the change in velocity. This equation represents one of the primary principles to be used in the analysis of collision during this unit. On our previous topic, we tried to relate initial momentum to final momentum. But this formula can also be used to also solve problem involving momentum and collision. Now, to truly understand the equation, it is important to understand the meaning in words. In words, it could be said that the force times the time, this one, the force times the time, equals to mass times the change in velocity. In physics, the quantity force multiplied by time, here, force multiplied by time is actually also equal to the term impulse. Okay? So I is equal to the term impulse. So the force when you apply through a time is called impulse. If you can recall our example a while ago, if you try to push a slowing down truck in a certain period of time, you are going to produce impulse, and impulse will change the momentum. And since the quantity mv is the momentum, m and v must be also the change in momentum. So the equation really states that impulse is also equal to change in momentum. Since I is equal to ft and ft is equal to mv, we can also write down I is equal to m delta v. Remember that do not mistake the following. The first one, this is the definition of impulse when you apply a force on a certain period of time. However, as per our equation here, they equate to each other. This one here, this formula here, actually discusses the consequence or the result, quote unquote, of impulse. Because when you apply a force on a certain period of time, your result will be the change in velocity in a certain mass. Bakit, sir, walang change in mass? Kasi usually when you, for example, stop the truck will not change its mass unless, for example, may mga natanggal na parts. But of course, that's another topic. Usually, if you apply an impulse on an object which has a momentum, mass will retain, and then ang magbabago lang would be its velocity until it comes to a halt. One focus of this lesson 5, is to understand the physics of collision. The physics of collision are governed by the laws of momentum. And the first law that we discussed in this unit is expressed in the previous equation. This equation is known as the impulse momentum change equation. Okay, let's write it down again. I is equal to F multiplied by time, or mass multiplied by delta V. So we can break it down into I is equal to Ft, or I is equal to m multiplied by delta V. The law can be expressed this way. In a collision, an object experiences a force for a specific amount of time. The result is the change in momentum. The result of the force acting for the given amount of time is that the object's mass either speeds up or slows down or change in direction. The impulse experienced by the object equals the change in momentum of the object, or simply this equation. In collision, objects experience an impulse. The impulse causes and is equal to the change in momentum. Consider again a football, halfback running down the football as seen in this video, and encountering a collision with a defensive back, such as this one. Kindly watch. And he's running, however, yung naka-cream, binangga siya. The collision would change the halfback speed. As you can see, medyo bumagal siya. And thus, his momentum. The motion was represented by a ticker tape diagram. So, itong mga nakita nyo ganito, that's called a ticker tape diagram. So, as we can see here, on this part here, same amount of time. However, it can here, it can take a lot of distance, which means the velocity is higher on this part. However, on this part, nung binangga na siya, impulse was applied, and for a certain amount of times, we can see here, mas lumiliit yung distance traveled of the ticker tape. Until, eventually, for example, kung yung naka-cream kanina, niyakap niya tong lalaki na to, what will happen is that it will eventually come to a halt. So, babagal ang babagal siya. Ito, this represents the change in momentum. At approximately the 10th dot of the diagram, the collision occurs and lasts for a certain amount of time. And in terms of the dots, the collision lasts for a time equivalent to approximately 9 dots. In the halfback defensive back collision, the halfback experiences a force that lasts for a certain amount of time, and that changes his momentum. Since the collision causes the rightward moving halfback to slow down, the force on the halfback must have been directed leftward. Sabihin, if the momentum is moving to the right, the force applied kanina is moving to the left. Katulad nung kanina. Diba pa-left yung naka-cream? If the halfback experienced a force, for example, of 800 Newton for 0.9 seconds, then we could say that the impulse was 720 Newton per second. Let's write it down. So the impulse is equal to Ft, and if this halfback here, nung binangga siya pa left with a force of 800 Newton for 0.9 seconds, the halfback here experienced an impulse of 720 Newton per second. This impulse would cause a momentum change of about, let me change the ink, of about 720 kilogram per meter per second. Okay. In a collision, the impulse was experienced by an object is always equal to the momentum change. So equal momentum change. So this is the momentum change, this is the impulse. So they are always equal. Okay. I hope that's clear. To understand this better, we're going to have some examples here at the screen. You may get your calculator, your extra notes, so you can follow along while we try to solve this one. So this is example number 3. for momentum, collision, and impulse. So let's read first our problem. A 4 kilogram object moving 5 meters per second east was hit by an impulse of 10 kilogram meters per second to the east as well. Find the final velocity of the object. So that's our problem. So let's illustrate. We have here a 4 kilogram object. Let's call this M. And M has a mass of 4 kilogram, and it's actually already moving for about 5 meters per second east. So that would be a positive value. And then suddenly it was hit by an impulse of 10 kilogram meters per second. So also to the east. Parang, for example, when you're driving your car, then may bumangga sa likod nyo. That's what happened. The impulse of 10 kilogram meters per second. Yan, so binangga siya. Our question, this is our illustration, our given. Our question is, we're trying to find the final velocity. What's the final velocity of the object, or M? So let's write it down. Again, our formula for impulse is I is equal to Ft. This is the definition. However, we are going to mostly use I is equal to M delta V, since this is the formula with the final velocity. With velocity rather. Okay, so let's write it down. I is equal to M delta V. Now, we want to isolate delta V. Okay, so to do this, delta V again is the change in velocity. So that's Vf and Vi actually. So to do this, we have to divide both sides by M. Cancel, cancel. Our formula would be the change in velocity is equal to I over M. From this, we'll just have to plug our value. I, or the impulse, is 10. I'm not going to write the units anymore. That's kilogram meters per second. And our M, or the mass of the object, is 4. So yeah, let's write our unit. Kilogram meter per second. Then we have here kilogram. This will cancel. Our final unit for our delta V is meters per second. 10 divided by 4 is obviously 2.5. So that's 2.5 meters per second. Now, how do we find the final velocity? Remember that the definition of delta V is actually final velocity minus initial velocity. That's the change in velocity. For short, Vf is equal to, when we try to isolate Vf here, what we'll do is to transfer the other one to the other side. So we're going to have positive Vi plus delta V. Okay, so from here, Vi is the initial velocity, and that's given. This one, that's initial velocity of the object. That would be 5 meters per second plus the change in velocity, which is 2.5. So 5 plus 2.5, that's simply Vf is equal to 7.5 meters per second. So that's how you do it. So you now solve for the final velocity of the object, which is 7.5 meters per second. Okay, pretty simple. Next. Okay, so next problem. We still have the 4 kilogram object. It's still moving 5 meters to the 5 meters per second to the east. However, this time it was hit by an impulse on the opposite direction. So let's illustrate that so we can visually see. We have here the object M with a mass of 4 kilogram, and it's moving to the east, what's to the right here, with a velocity of initial velocity of 5 meters per second. Okay, so kanina hindi siya gumagalaw. I mean, kanina the impulse hits it from behind. This time, sinalubong siya. and it's actually quite large. The impulse is negative 40 kilogram meters per second. Okay, so our problem asks us to search for the final velocity. Same as the last time. Okay, so to do this, we still have to write down the definition, the consequence of impulse, which is the change in momentum. I is equal to m over v. We have to isolate delta v because we're trying to find for the change in velocity, because the change in velocity is actually equal to vf minus vi, and by searching the change in velocity, we can by searching for the change in velocity, we can actually isolate vf, and we have our vi, that's 5 meters per second to the east. So that's how we do it. Okay, let's try to isolate first delta v. Dividing both sides by m, we're going to have to cancel that out. Delta v is equal to I over m. Our impulse is negative 40, and our mass is, of course, 4 kilogram. So our delta v is equal to negative 10 meters per second. So, dali lang. Now, trying to isolate vf, we have to transpose both the negative vi. So that will be vf is equal to delta v, vi plus v, or delta v. So vi is given as 5, and delta v, we have searched that, and that is negative 10. So that will be negative 10 here. Computing for the final velocity, you're going to have negative 5 meters per second. Okay, that's it. These are fairly easy and theoretical problems. On our future installment of this discussion, we're going to discuss real-life scenarios, such as, for example, what's the difference between if a modern car and an old car hits the wall, something like that. Okay, last example for impulse. This time we have a 2 kilogram object which is moving negative 5 meters to the west naman, and it was hit by an impulse of 30 kilogram meters per second to the east. Find the final velocity of the object. Parang kanina, same as the problem a while ago, but this time, binaliktad siya. So, let's try to write it down. We have here an object with a mass of 2 kilogram. It's moving to the west. So, its velocity would be negative 5 meters per second. And it was hit by an impulse to the east. The impulse is quite large also. It's 30 kilogram meters per second. Still searching for the final velocity. By this time, I know you already know what to do here, but just to be sure, let's write it down. I is equal to m delta v. Isolating delta v, you're going to have I over m. Our I is 30 and our m is 5, negative 5. Sorry, our m is 2. Because that's the mass of the object. So 30 divided by 2, you're going to have 15 meters per second. Definition of delta V is equal to Vf minus Vi. Okay, so Vf would be equal to Vi plus delta V. So Vi is initial velocity of negative 5 plus a positive 15 from delta V. So you're going to have here the final velocity of 10 meters per second. So that's your final velocity for this problem set. Okay, so for this one, we're going to discuss what we call the rebounding collision. So Consider a collision of a tennis ball with a wall. Now, depending on the physical properties of the ball and the wall, and then the speed at which the ball rebounds from the wall upon colliding with it will vary. The diagrams below depict the changes in velocity of the same ball, both this one here and this one here. So we are going to try to find out the concept here: greatest velocity change, greatest acceleration change, greatest momentum change, and greatest impulse. So what we're going to do is to try to find out if it's greatest velocity change in case A, or is it the greatest velocity change with case B. So we have two cases, case A and case B. Okay, so case A goes to the wall, papunta siya sa wall with a velocity of 10 meters per second. And then after that, bumalik siya ng 5 meters per second. So ibig sabihin parang ano na to, medyo malambot na yung tennis ball. However, in case B, it hits the wall with 30 meters per second, medyo mas mabilis din. And then medyo mas solid pa siya, no? Bago-bago pa. And it umalis siya sa wall, it rebounds sa wall about 28 meters per second. Between case A and case B, which has the greatest velocity change? Alright, answer for greatest velocity change is case B. The velocity change is greatest in case B. Remember that the velocity changes from a positive 30 meters per second to a negative 28 meters per second. So remember again that velocity is a vector quantity. This is a change of 58 meters per second negatively and is greater than the change in velocity of case A, which is negative 15 meters per second. Okay? So wag kayo malilito. Again, this is a vector quantity. Next, for the greatest acceleration, the answer is still case B. Acceleration depends on the velocity change, and the velocity change is greatest in case B as stated on our previous scenario. Remember that acceleration is the change in velocity over time. How about the greatest momentum change? Still case B. Momentum change depends on velocity change, and if the velocity change is greatest in case B, automatically the greatest momentum change will also be case B. How about impulse? Still case B. Impulse change, impulse is equal to momentum change, diba? I is equal to m delta v. And if the momentum change is greatest in case B, automatically it will also cause the greatest impulse on the scenario. So still case B. For the sticker tape diagram, we don't have any value here, but I'm going to give you a few moments. Kindly answer the 4 questions. Type down on the comment section on the chat panel your answer. Sunod-sunod na lang sa apat. Case B, ganon. Case A, case A. Your time starts now. Okay, so this time we don't have any value, but we have a ticker tape diagram. So for the greatest velocity change, the answer is case B. In each case, the initial velocity is the same. How would you tell? If you're going to look at the ticker tape, the dots are fairly um, here. The dots are have the same distances with each other. In case B, the object rebounds in the opposite direction, as we can see here, with a greater speed than case A. This is equivalent to a change from a positive 10 meters per second to negative 5 meters per second. Whereas case A has a change from positive 10 meters per second to a negative 2 meters per second. So either you measure that, however, just by looking at it on a ticker tape, you can see that this has a greater speed. So if it both have a greater speed, you're going to have greatest velocity change from positive to a negative. For the greatest acceleration, the answer still will be case B, since if you have the greatest velocity change on the case B, and acceleration again is equal to velocity change, so case B pa rin yan. Greatest momentum change, case B. Why? Again, momentum change is equal to the change in velocity, and the higher the change in velocity, the higher the momentum change. Last one, impulse. Case B pa rin, since impulse is equal to the momentum change, and if you have higher momentum change, you're going to have higher impulse. So I hope by this example, we have garnered some kind of information, or medyo na-gets na natin on what's the connection between those different variables. Okay, so observe that each of the collision above involved the rebound of a ball of a fall. Observe that the greater the rebound effect, the greater the acceleration, momentum change, and impulse. A rebound is a special type of collision involving a direction change in addition to a speed change. The result of the direction change is a large velocity change because, again, from positive to a negative. On occasion, in a rebound collision, an object will maintain the same or nearly the same speed as it had before the collision. Collisions in which the objects rebound with the same speed, thus the same momentum and kinetic energy, are collisions known as elastic collision. So usually in real life, this does not happen. Now 100% all of the kinetic energy are transferred, but just for theoretical reasons, we are still going to try to compute them. In general, elastic collisions are characterized by a large velocity change, a large momentum change, and a large impulse and a large force.